Hello. So hope everybody's having a good time. Take it on. You need to. Okay. Can everybody hear me all right? Sometimes I talk too loud, but I think it sounds good now. So today, my goal is to persuade everyone to take a look at the Netsniff-ng Toolkit. And we're going to go through a bunch of examples and some features of the toolkit. And hopefully we have some developers in the crowd. I'm not so much of a developer, but I am trying to learn various things like C. And maybe we can convince some of you to contribute back to the projects. I think there's some really interesting things going on in here. Okay, so I actually, in my biography on the website, it says I was an admin for a small business. Well, actually I just took a new job, so it's been a rush getting all my stuff together too. I just moved a few months ago, so I'm now at the CSA, which a few of you may be familiar with is for our involvement in the Bro project. The Bro network monitoring platform, we work on that, so that's pretty cool. And there's a few other things about me. I do a lot of documentation mainly for the Netsniff-ng Toolkit. Okay, so let's get started with the topic. So it started in 2009, and it's basically done out of the free time of the two main developers. There's been some work where I've had a few other guys from industry where their reporter would help them do labor time to contribute back if they needed something useful, like wireless RF monitoring and such things like that. So it's basically been people contributing in the free time like most projects. And even though it started in 2009, it's still in its infancy. But now we're at a good point, which we'll talk about later, and to where we're developing, or it's at the point where there's a lot of features, very stable, and so on and so forth. So you can use the toolkit for network analysis, packet sniffing, traffic monitoring, security, all kinds of stuff like that, performance metrics. So the toolkit has a bunch of tools, and today, you can quickly read over these if you need to, we'll talk about 4 of them: Netsniff-ng, TraffGen, BPFC, and FlowTop. And those are the main ones, particularly the Netsniff-ng, TraffGen, and BPFC, but we'll mention FlowTop briefly. So this is the big picture. So if you want to categorize this and what each of the tools do, this is how you would do it. This is a nice little graph that one of the guys created. So over in the traffic capturing and traffic generation areas, this is where we'll mainly be staying and talking about. So this is basically, we use in Netsniff-ng, we use memory map buffers using on the PF packet sockets, where the packets are memory mapped from kernel space to user space. You don't have to do extra context switches or anything like that. So this is about the best performance you can get from user space. And there are third-party drivers like the MirrorCom, Sniffer-ng, and you guys may be familiar with PF-ring, DNA. Those tend to outperform because they do custom things, and they have specific cards and drivers for those cards to get extra performance. So one cool thing about TraffGen, which we'll get into, is you get entire control over the packets, all the headers, all the data, and the toolkit is optimized for Linux. They're not interested really in porting, but if someone else will do it, they'll probably gladly accept it. But it's optimized for Linux, and it has a very small code footprint. So, and like I said, here we're at a good point in its life cycle. The reason it's optimized for Linux is that the core developers of Netsniff-ng are kernel devs. That's what they do. So they're usually on the latest feature of the kernel, and you can see them on the kernel list contributing back. And I'll go through a few of those. And if you're wanting to get into some usage examples, some of the latest features in the kernel, a good idea is to actually just review the Netsniff-ng code, because they usually integrate it when they find that it fits, and it's there right away. An example of this is tpacket v3. So this is a new structure for packets, and it was developed by Chetan Lok, and it replaces tpacket v2 in the kernel. And basically, the results, which is the important part for many of us, is just that there is a 15-20% reduction in reported usage in CPU usage and a 20% increase in packet capture. And the only sniffer that has this that I'm aware of right now is the Netsniff-ng Toolkit. So Netsniff-ng is the sniffing tool of Toolkit. And any program that uses libpcap is using tpacket v2. Because they're using that library, that's what they have to use that version. So, and there's a few reasons at the bottom. So packet density is increased, packets are closer together, and there's less misses in the TLP. So CPU can have more time to processing without missing it in cache. So another development that was recent, I believe this is from Daniel, one of our core developers in the kernel, is this neat little BPF instruction. This allows someone to, it's a dynamic instruction, to actually write packet headers to disk with just truncate the payload, just skip it, which is pretty cool. Because before you would have to do probably some math, you want to do it in the entire header, you know, the 20 byte IP header, blah, 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 the 8 byte UDP and stuff like that. But now you can just enter this and dynamically does that. And basically at the bottom, in the example, we have you load this value, whatever the value represents, OFF, that's what they're calling the instruction, BPFC. You return whatever's in the accumulator, that'd be the value return that basically specifies the size of the packet to return. So, which is pretty cool. And again, the PCAP does not have this, and BPFC is the only one aware of that does, unless you just write your own code to do it. So, and this is a new thing. This is also done by Daniel, where they actually have a netleak monitor. So you can actually, they have netleak, so you can actually sniff on a PF packet socket and listen to netleak messages, which basically is how programs talk between kernel space and user space. So this is packet analyzer neutral, so we're actually going to have a plan is to have a dissector sometime in the future, so people can analyze those messages in Netsniff-ng. Okay, and let's get to Netsniff-ng in particular. So it's an analyzer, recorder, replayer, and you'll see this on the website, the man page. It uses the PF packet socket and map, RX, and TX ring. At the time it came out, it was the first tool to use that, so you'll still see using it. I guess it's not too much of a big thing anymore because like libpcap and all those tools that rely on, they use, because of that, they use the RX ring. Anyways, so it is now Netsniff-ng is the backend recorder for Security Onion and Explico and the Network Security Toolkit distribution. So if you're using Security Onion, I'm sure there's a few users in there. Anybody got their hands? Raise them? Yes, awesome. I love Security Onion. So you're using Netsniff-ng in there as well. And we support, our Netsniff-ng supports a few different I/O methods, which is nice because a lot of the tools you don't get the different I/O methods. And we have read-write, most of the tools use that. The standard read-write calls. Here, Netsniff-ng defaults to scatter-gather, which is a little faster, because it bundles up calls and uses vectors. And nmap is another faster than sequential I/O, or it is sequential I/O, I believe. And that's if you can fit things in RAM, you should use nmap, because you'll get better performance. And we also, the Linux kernel has the JIT compiler, and it's not enabled by default. So when you run Netsniff-ng, what will happen is it'll enable the JIT compiler. It's just a setting in procfs, or you can use syscontrol if you just want to add it to the file. And basically what the BPF JIT compiler does is that it creates a JIT image based on native code, or native based on your architecture's code. So it's native. And then the result is that it compiles that, and every time a packet comes in, that gets executed against that code. And then because the code is based on your native underlying architecture, you get about, it's estimated about 50 nanoseconds extra performance over the normal BPF compiler. So if you use JIT, you get a little better performance and execution of the packet. So. And it also does some basic OS tuning for reception whenever you run Netsniff-ng. It'll go through a few options in procfs, like the RMEM and defaults and max settings in the WMEM, which basically just controls software memory buffers, and it increases the sizes. Okay, the Linux kernel supports a few packet types. So basically when you're calling the socket, you can say, oh, here, apply only host traffic or broadcast traffic or multicast traffic. And in Netsniff-ng, you just add the -- type. You get outgoing, others, multicast, broadcast. So you don't have to do a BPF filter, really. You can just apply these types and get the same result. Okay, so we've got a few examples here. The first one just shows a basic usage and how if you want to do full content daily capture, you just say, hey, First, I should note that it's really easy, so you just have in and out. It's pretty much the things you need to know. It's pretty intuitive. So in on this interface, out to this directory, in that case, it's just out to pcaps. And we use silence because we don't want to print the packet to the screen, because that will cause a number of interrupts because it's got to print to your terminal. And then we allocate a RAID buffer size of 2 gigabytes. And so in this example, we say, hey, we're going to run it as high priority. You can also recognize if you're run it random. And then we say we're going to run it at an interval of 24 hours. So every 24 hours, we write out a PCAP. So you have daily PCAPs, which is kind of cool. So got that built in. Here's a few other examples. We can use RF raw. So that basically puts your device in a monitor mode for using wireless. You can sniff raw. And we can also replay from interface to interface. And at the bottom, I'm going to show a few examples of applying filters. And I will mention that Netsniff-ng does not completely rely on libpcap in the sense that it is compiled with libpcap, but we don't use the libpcap calls to open a socket and read in packets and so forth. We actually just use it if someone wants to specify a high-level libpcap filter, like TCP and port 22, like I have listed. It'll actually just go to libpcap and compile that. So otherwise, you can use BPFC. Okay, here's a little output at the bottom. I'm not sure how readable it is from up here, but generally we have at the top, you use the verbose option. It gives you a few things, like how many frames can fit in the buffer and so on, based on the size of your buffer. And you can see the dissection in the middle box. And it also has GeoIP built in, so at the bottom you can see, you may be able to see, it says that it detected a location in Sydney, Australia for the destination, which is kind of cool, so that's built in. And the statistics, it gives you, which everybody's quite familiar with, incoming pass filter dropped, and then a percentage in the capture duration. Okay, so let's go to TraftGen. TraftGen is a multi-threaded number generation tool. And basically, you create a packet based on TraftGen language. It's got a few expressions. You basically just specify the hex values, and you can generate the packet out the interface, which is kind of cool. It's more flexible than that, though. There's a few macros and things that make things easier. And here's a test that the developers did whenever Daniel was doing his thesis on traffic generators. And you can see PacketGen is well known as one of the fastest one if you don't have a hardware generator. It's a kernel module. And you can see that TraftGen is fairly familiar with it. Not quite there, but very close. And is anybody familiar with PacketGen? Okay. It's a pretty cool in kernel modules in the source tree, so when you install the Linux kernel, you should have it installed. You can just load the module, and then I'll give you a few examples. But let's take a quick dichotomize this and give a quick overview of each one. So PacketGen is typically faster on small packet sizes and nearly the same otherwise. TraftGen is not quite as fast on the smaller sizes, like 64 bytes and 128 bytes. But as it rises, as the size rises, it's much easier to generate traffic because it is hard to generate small packets at a fast rate. And here's an example. On a 64 byte, on one of my tests, I was generating 520,000 packets per second. And PacketGen during the same test was 620,000, so 100,000. And the cool thing about TraftGen, though, one thing it has as an advantage is that the entire packet is customizable. The payload, everything, and that's not the case with PacketGen. You have a few options, and then you cannot really go any more granular. So you can check that in a second. And then PacketGen is configured by sending commands to ProcFX. So it's usually a shell script that floats around the internet. Uses the PacketGen commands. You just set the command or the number of packets you want, all that. And the shell script does it. It just basically echoes values to ProcFX, and you can find that on the web. Where in the case with TraftGen, what we do is we have a configuration file, and basically we just say, hey, we make these delimiters, anything between these 2 points is going to be our packet, and then we just type the values in, and then we generate it. And here's an example. This is using a 64-byte frame of PacketGen, and here's me not using the script. I just figured I'd show you how that normally does. So just echo these values, and here you have source MAC, destination MAC, UDP ports, min max port. So you can do ranges. Here I don't want to do ranges. I want to generate the syslog 514, and that's basically how much granularity there is with PacketGen. However, with TraftGen, we can do this, which is cool. Now, this takes a long time doing things like this, obviously, but with the macros, we can speed it up. Now, here's some performance. performance metrics. This was at my house. It's got a server I was using lying around. It's approximately 6 to 7 years old. So I know that it's reported from multiple people that we can do line rate, 1 gigabit line rate with TrackGen. I don't want to work any 10 gigabit per second performance metrics yet, but if I get my hands on some stuff that are on modern machines, I do have an example at the bottom, but like I said, my machine's 6 to 7 years old, still PowerEdge. But here's what I have. You can see if you look at the 1 gigabit rates, we have, with the 64 and 120, you can see how the line rate percentage increases. So with 64, we have 24% of the traffic generated was at that line rate. So, and we see that we're nearly we are nearly line rate as we get to 256 and above. So we get pretty close in the 90% range. However, in 10 gigabits per second, it's much, much harder. And I think on my test with packaging for that 64, packaging would have 3% with TrackGen, but I was able to double that with packaging. I was able to get 6% of line rate with packaging. Okay. 10 gigabit again is pretty hard to do. Okay, so let's look at a few TrackGen examples. So the first example we have, we're sending 15 million packets from reading in from this config file. That's called the 64.cfg, and we're outputting it to E2. And that's really all there is to it. So it's pretty simple to use. So once you have your configuration in place, you just hit enter and they're out. I've sent out the interface. And then we also do mortality tests. So basically, if you want to fuzz a kernel or a network stack, you can do that. And you can also do with there's an option for setting a seed. And then basically, after it runs, it'll test, it'll do like an ICMP echo and see if the kernel responds still. So. We can also generate raw 802.11 frames, which is nice. So you can do your raw 802.11 stuff like beacon frames. You can just send those out, which I have a script. I'll show it closer to the end, where I've written something like that. We can also pass through STDN, where we say TrackGen-E. That's a built-in TCP configuration. So basically, what we do is we just pipe that into TrackGen. We specify on the next instance through the pipe that in, you put the dash. It's going to read that configuration from standard in, and then we'll output it. And here's a little look at the TrackGen expression language. So we have these macros. We can fill, random, dynamic random, constants, different ones. We got incrementers and decrementers. And we have a few examples here. So if you look at this under the macros, number 2, fill. So we can fill, an example I have hex FF. So the full byte, all the bit sets, and we want to generate that 10 times. So 4 n bytes generate this. And you can, so if you want to generate a 64 byte packet real quick off top, instead of doing a whole configuration, all you have to do is say fill 0xFF, comma 64. And then you generate that. You got 64 bytes of FFs. So not bad. So for different types that TrackGen accepts, we have decimal, hexadecimal, octal, binary, and characters and strings. So we can specify things in other ways. You don't have to use hex. This is nice. Again, we can actually use the C preprocessor by passing the -CPP option, and then we can use definitions. When you see definitions, we can include, TrackGen comes, when you install the Netsniff-ng Toolkit, there is a file, stddef.h, that has a bunch of definitions already. So you can just include that. And the example at the bottom I have where you have the protocol field in the Ethernet header, eth_p_ip. So if you don't know that you want to put IP above, you can just put in that definition. And it'll translate it. So here's how you, this is basically a packet definition up here. You have the curly braces, beginning and ending, and the packet data goes in between. Not too bad. So here is that example I was talking about earlier. If you want to read 64 byte packet of all Fs, here you go. This is all you have to do. Stick it in the file and tell TrackGen to read it. And we have this one. This generates 512 bytes of random data. And you can use your scripting languages. So if you guys want to make your own configs, like here's an example of Python. Just kind of using Python print statement, just to print the brackets, new line, and then add the data, and then multiply whatever it has at my packet times 8, so that string 8 times. And basically this, so that's some other guy. And then all you have to do is send that with TrackGen, and then here I use Netsniff-ng to read it in. And you can see that whenever there's the ASCII translation at the bottom for the characters, you can see my packet, my packet, my packet. And the beginning part of it is actually in the source, and or the source destination MAC address. So that's the other parts. That's why you see the cut off the ET at the beginning. So pretty neat. And here's a little more advanced trap-gen expression. So here we can actually tell trap-gen, hey, you know, what CPUs do you want to use? Here we use 0 through 3, so 4 CPUs, being an index 0. And we say Ethernet, we want to generate 12 bytes, so the source and destination Ethernet max hardware addresses. And then we say, hey, after that, we want to use the IP protocol field, so we specify that in there. And then we want to generate a IP header of 20 bytes, random. Question's going to be valid, but hey, we can do it. And then we'll do the header of 8 bytes. And then for the payload, data, we'll for 1472 bytes of random. So the random functions are good for functions. All right, so here's another example. It's a little more advanced. So basically what we're using is the built-in function here. See the top says trapgen-e. Well, this is the built-in TCP example, and it has a full-length packet that is valid. You can send this out, and it shows that we include the stdef file, the header file, and then we fill in the destination MAC, source MAC, protocol field, IP version, the international header length, the type of service, the total length of the header, and so on and so forth. And we actually got a macro for checksum, so you can just do csum IP and then specify the values based on the size, TCP ports, blah, 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 and we can set the flags. So we use bit shifting over here, a little more advanced, but all that can be done. Now, if you want to use them in conjunction, our PCAP2 trapgen, this is nice. If you have a PCAP file, I'm sure many of you are familiar with TCP replay, well, you can do something similar with trapgen and Netsniff-ng, or with Netsniff-ng. What we'll do is, first, we'll have the PCAP, we'll write to disk, and then we'll pipe it out to trapgen. And you can apply a VPF filter in the bottom. I say, hey, read in this PCAP file, packet.pcap, send it out via STD out, and we want to take one packet of it, and then just we want to use the VPF filter for the first TCP packet in the packet file, and we pass the trapgen, and say, hey, generate that packet 1 million times, and we do. And we're hopefully going to have some more, we don't have, as far as the TCP replay, where you get all the specific options of the performance, like the speeds and all that, we don't have that granularity of trapgen, and that may be something to think about. So, just FYI. Gen config is a little shell script I wrote, and basically what it does is I have a bunch of packet or a few packet configurations that I created, and I just stick them in there, and then I just pass some options to the command line, the arguments, and say, hey, I want my source IP address to be this, my destination IP address to be this, my MAC address, blah, 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 import. And then it'll generate a custom configuration. I did for performance metrics, if you guys ever want to do that, I did the RFC 2544 Ethernet size frame steps. That's the benchmark methodology for Ethernet and a bunch of other network technologies. And basically, so if you just run that and you specify the IPs that you need to send to the machine and test it, it generates the entire set of 64, 128, 256, 512, blah, 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 packet sizes that are used for performance tests. So you can just do that. I have my GitHub link at the bottom, so you can check that out when you use it. If you want to contribute back and make your own configuration, or if you have something that's useful, just pass it back to me, I'll include it, or you can. All right, and I also have one thing that's kind of cool is the beacon frame generator. So if you want to generate, mass amounts of wireless beacon frames, you can do it. And I currently only have a 8-byte character limit because I didn't want to do the math, or I haven't done the math yet for calculating so that the header comes out valid and all that. But so you can do free Wi-Fi in that case, so you can send that out. And it's back to the performance metrics. So how would we want? If you want to do metrics, how would we proceed? Well, this is one way. We could do we use the RFC 2544 generation set for frame Ethernet sizes. We can use trapgen. We can basically say, hey, let's generate a bunch of traffic to a machine that we want to send it to, that we want to test the performance of. And then what we'll do is we'll run IFPPS, which is again included in the Netsniff-ng suite, but we'll talk about that. And that will actually measure the line rate as a nice option now. It's new, it's -P, capital P, where you can actually test the percentage of line rate coming in, so you can measure it that way. And we can then, if you want to do packet capturing performance tests, we can actually script, have Netsniff-ng run in a shell every 5 minutes or something, and have your trapgen instance transmit every 5 minutes, and then you have a script that says, hey, SIGINT every 5 or whatever, how long it's going to take to send the packets to the process of the snipping, so you can TCP up all of those if you want to test them. And then what you would do is you have that right to a PCAP file. You can use cap info, some awk later on just to pipe out, the loss metrics, all that. You can also pull the information from your driver. You can do performance tests that way. That's something I'm kind of working on. I haven't had a whole lot of time, but it will be done. So eventually I will have TCP dump, dump cap, build, daemon logger, Netsniff-ng tests and compare. So that will be coming out in the future. All right, so here's another example of the daily PCAP options. So here I put a lot more options, or Netsniff-ng options in there, just so you get an idea of a few of the things that I was working on the man page right away just for the presentation. So you can do prefixes. You can call it, hey, I want my package to begin with this word, my packet, timestamp, .pcap or something for each one, and just increments the timestamp. So things like that can be done. And here we can also set SMP infinity, IRQ infinity, and so on. So when doing high performance packet capture, I think that's what a lot of people are interested in when they hear of Netsniff-ng, or that's why they go to it. And it's very hard to do. I've done a few tests, and it's a lot of system tuning. It's really, really difficult. You have to do a lot of tests on different buffer sizes, network card settings, kernel settings, socket settings, so on and so forth. Even if you're writing a disk, like PD flush, and all those dirty ratio settings, you got to play with that. It's really hard to do, but here are some considerations if you're going to do some performance tests. One thing you should probably have is a network card that supports NAPI, the new application programming interface, which basically handles the interrupts better than they were handled before in throttling. Most modern cards have multiple queues, right? So we can use RSS, which is receive side scaling, and essentially, say a NIC has 4 queues, what can happen is the packet can be split to different queues. And we can use RPS. RPS is receive packet steering, and I have there's a document in the Linux kernel source tree in the documentations directory called scaling of TXT that explains all these. And if you don't have a card that supports RSS, you can use RPS as neutral, and where you can assign queues. You can actually take the packets in and have them flow or balance kind of over your different CPUs. So you can set that up. And other things to consider are offloading measures. Usually offloading is a good thing to have. Performance, interrupt throttling, coalescence, you should have multi-core CPU, lots of RAM, hardware locality settings, so you should check out SMP infinity, fastest configuration is very important, and so on and so forth. Don't spend too much time on that. And software configuration. So if you want the latest and the greatest, like all those new features I talked about earlier at the beginning, the Linux kernel, like TPacket v3, and the new BPF instructions, and so on and so forth, they are in the latest kernel. So you'll have to recompile the latest kernel and install it, and you'll be able to use those features. So when you're doing tests and you're doing your bleeding edge stuff, then it's good to have the latest kernel, the latest mainline for the latest fixes and features. So here's just a few options of our ideas you can use to set or to tune your system. So here we increase the memory buffer with syscontrol. We increase the queue length. That's the driver queue length by ifconfig. That's actually that's the queue disk length. I take that back. So we use the default is queue disk FIFO fast, PFAST, something like that. So you can set the value of that. Set IRP affinity. You can enable the JIT compiler yourself. Just echoing a 1 to the file and lock that, so on and so forth. And you can, if your disk is too slow, which is the case for many of us, you can use a RAM disk. So you can just mount a 20, here this is an example, mount a 24 gigabyte RAM disk, and then we can write to that. And then later on, move it over to your hard drive at night or something, and then travel it as RAM or something. And BPFC, so this is the Berkeley Packet Filter Compiler. I believe it is written to standard for the BPF paper that came out by Van Jacobson, and his name is escaping me at the moment, but I believe it follows it to a T. So we have support for internal Linux kernel extensions. So these are things that the Linux kernel supports that give you lower level filtering access to the packets, and I'll show a few of these in the next slide, I believe it is. A lot of the libpcap compiler does not have those built in, so if you want to use those extensions at the moment, you'll need to use BPFC to keep up to date on that. Also, we can use BPFC. You can use set comp filters. where this is something kind of new to me. I found this out too long ago, where it's Google Chrome uses this, where you can actually filter on system calls. So if you're using Google Chrome on Linux, that is, of course, this is a Linux thing. And so does SSHD, and I believe that's from the OpenSSH project, that SSHD. They use these as well, where you can actually apply BPF filters and filter system calls, which is really cool. So it's kind of like a sandbox. And then NetFilter actually has, or IP tables now, which you can use to access NetFilter, has a feature. You can actually type in or read in a BPF file, so we can generate a BPF compilation file, or compile BPF code with BPFC, and then pass it in IP tables. And it actually can output in the IP tables or NetFilter format. It's pretty specific. And here's an example. So we have a BPFC. We have a BPF file called ARP. They're basically compiling and taking the output and writing it to ARP.bpf, and then telling Netsniff-ng to read it. So this is also a really good tool to learn how to write BPF, because you really can't do that with the PCAP, right? You just specify the high-level filter and it compiles it. Of course, you can dump the assembler-like code, but here you can actually write it. So, like I said, some of the kernel extensions that can't be expressed in the high-level syntax can be done in this, and there's a lot of other things that are instructions that are out in the PCAP. So, and this is mainly used for kernel devs to do network development. Like there's bugs found, and they'll use this to test this compiler versus a different one. So, and here's some of the BPF extensions. So you can use packet length, you can get the proto, which is the ETH type field, type, POFS, when we talk about detecting the payload, interface index, VLANs, queues, CPUs, and hashes. There's RX hash points. You can, if you're using RSS, which is what I was dealing with, it generates hashes to validate the traffic. You can actually filter on that hash. So here's how you compile it. So at the top we have on the PCAP equivalent. So we say ether source, and you want to read in this MAC. Source address. So A, B, C, C, D, E, F, F. PC one will follow. And in BPFC, this is what I want to do. I just create a text file, and I say load LD. This is going to load 4 bytes. It is a word at the 8-byte offset, which in Ethernet, the frame, it begins with the destination MAC address first, then the source. So we're going to filter the source. So we want an 8th in, and we'll have 4 bytes left because the Ethernet MAC address is 6 bytes. So basically that part will load the 4 bytes, as you see in the next instruction. It says just, or jump if not equal. So if it's not equal, then we'll go to the drop instruction, which is at the very end of the chain. At the very bottom, we say if it jumps to that, then we're going to return 0 length of the packet, so don't return the packet at all. And then if it is equal to C, C, D, E, E, F, F, or MAC address, then we'll jump to the next instruction, which is load H. We're loading a half word there, 16 bits, 2 bytes, and we're loading the other 2 bytes. This is based on the Indianness. So AABB, that's the rest of the frame, or the MAC, source MAC portion of the frame. And if that is equal, then we return 1514. If that is not AABB, then we'll return nothing. We don't max the packet, we don't return to these. And this is what happens after you compile, so you get the ugly outcomes. When you use TCP dump, we use -T to dump high-level filters to outputs as well. And here's an example using a kernel feature or the extension. This is actually the filter on CPU. So we load the CPU value, and we say jump if it's equal to CPU 0, then we'll return, and -1 is just another way of saying return the entire thing, no matter what the size. So we don't say 1514 where the frame is even bigger than that using general support, and -1 returns the entire thing, no matter what. Otherwise, if it's not CPU 0, then we'll return it. So, and the example use case for this is if you're using RPS where packets are distributed across different CPUs. You could then use the filter like this to say, hey, I just want to grab the packets that arrived on this CPU when they're distributed. And then to run this FNG, you say, hey, take it in and apply it. And it compiles in the kernel, and you get your packets. And here's some notable examples. So where the Netsniff-ng toolkit was used. And 2 examples that I'm aware of is that one of the kernel developers found a performance problem in the fragmentation done in the Linux kernel, and they were able to use TrapGen to create the packets to test that. And then later on, they encountered some problems, they made a patch for it. And BPFC was used to prove and exploit a x86 JIT bug. So plug in the JIT compiler, someone used BPFC, and found out that it didn't match. That whatever that was compiling in the JIT into the BPFC didn't match, and it turns out there was a bug in the JIT. So IFPPS, or IFPPS, is another cool tool that just reads stats. And it reads it directly from the kernel statistics, all the proc files. So, example, if you want to look at your network statistics, you can just do a watch on cat-proc-net-dev, and that's got all your receiving packets, the bytes, the drop count, the errors, the frames, all that. So you can just read directly from there. And that's what IFPPS does, along with a number of other places in the kernel, like soft IRQ, and proc interrupts, and so on and so forth. And with this, since we don't rely on another tool, we're doing directly from the kernel statistics, and we don't use a library to make other calls, we actually get more accurate results under high speeds, high throughput. Because an example was on one of the devs machines where they were generating line rates on 1 gigabit Ethernet. IP track, which uses lit PCAP, was only recording 246 packets per second, whereas since they were reading directly from the kernel stats, IFPPS reported the full line rate. And you can use this in conjunction. Basically, all the stuff that you find using the normal system images like VMstat, all that stuff's printed here. So you can monitor context switches, idle time, CPU time, idle wait time, all that stuff. So you can, when you're using network traffic performance or measure from that, it's really nice to target. You can output it to the new plot format. So here's a look at IFPPS. This is not really too fancy right now because this machine just has a single CPU. And as you increase with hardware, the display gets bigger, you see a lot more stuff. So that is generally IFPPS. It just runs at an interval, and the default is 1 second. And we can actually output the CSV, which technically is not CSV, that's what they call it. And basically it's a white space delimited for GNU plot. And here's an example where I'm reading a IFPPS CSV file, and I'm just saying, hey, print all lines that match the packets per second, which is the third field. And here, we can use GOP, because it has a timestamp function, where we can say, hey, reading this timestamp and convert it, so by default it's unity clock time. And here we say, hey, print every line or interval that matches, or where the drop count is greater than 0 and the errors are greater than 0. So we want to know if we drop packets for our testing interval, and we can see here at the time we converted it, and blah, blah, blah. So you can hack that easily with GOP if you need to. And here's a quick GNU plot chart of a test I did. And excuse me, if you want to play around with that code at the top, this I've just begun to use GNU plots. These are fairly rudimentary. But essentially, we're just hitting a run, and we are. You see the chain or the top green line as it goes over. That's where the TrapGen ran start, and from another machine. And this is on the capture machine. This graph is generated from those stats. And we got about 650,000 packets per second, and then we had a loss of like 50,000 drops from the kernel. So you can graph that, and we can go a little further with the same file generally, and just say, hey, look at the drop count, and you can see that it's a little less than 40,000. So then you can show that you can put the time on there, and you can correlate it with IFPPS stats to see, if it's a CPU time spike, move the cron job in the background, if it's a CPU time or something at that time. So you can just correlate all that information because it's written. And then the other tool we'll talk about is FlowTop. So FlowTop is a top-like NetFlow viewer, or connection viewer. It uses NetFilter. So basically, you would say an IP tables command, you can say, hey, pass in all this traffic, and you run FlowTop, and just anything that comes in that patches that match rule, and it links, or that's how FlowTop basically calls it to NetFilter. And basically, it actually gives you a nice little flow. This could be good for instant response, by the way, because it actually tells you what program on the machine that you're running it you have to generate the traffic or is receiving the traffic, which is really cool. So I appreciate that. And eventually, there's going to be some new features on here, like sorting on bytes, packets, and all that. So it also does geo-IP location. As you can see, we have Sacramento, California, and Mountain View, and so on and so forth. So it's great. And to install Netsniff-ng, if you're running Ubuntu, this is generally all you need. So let's put this slide up. Not too bad. And what could be next? Well, We have a few things that are going to be worked on. One thing I'm kind of excited about when it comes out is the packet fan out, where you can fan out packets to multiple sockets, have multiple listers, and distribute the load of packets across multiple instances. So it's something that we look for that's fairly new in the kernel too, so I don't know what the stage level that is. And then basically pretty much everything else I mentioned with the flow top and Python packet counters, and there's going to be Mausaton. That program is a nice HP-like program where you can generate packets at a higher level, so you can generate stuff. And it's got a bunch of dissectors built in, so where you just say, hey, I want to generate a systolic packet, I specify the facility, the severity, blah, blah, blah. You simply send it out. So you can do cool stuff like that. And that is a tool that's been picked up. The man that developed it originally passed away 2 years ago, and so they're trying to integrate that into the toolkit now, taking up his code. So it still needs to be improved. And there's a bunch of links if you guys have any for more thorough research information. Go to those. And if you want to look for flight configurations online, not a whole lot there yet, but if you use those Google dorks at the bottom I put on there, you could probably find some filters or some TrackJet files. All right. Do I have any questions? No questions? All right. Well, I hope you guys check out the toolkit. If you have any questions, do email me or email the list. Preferably the list, unless it's more personal to my talk. And I guess that'd be about all. Well, thank you guys.